Welcome everyone to the world of multi-armed bandits, and we will take a look at a particular algorithm, namely Thompson sampling. And Thompson sampling tells us how to update our priors about rewards. And to understand Thompson sampling, we need to check out some notation. So here we need to distinguish between the rewards that we get after each experiment. So that's the R for each arm A at time step T. And the average reward that is unknown that we need to estimate, that's the Q of A or the capital R of A. And the idea of Thompson sampling is to draw from a distribution samples of potential average rewards. So here we have D draws of the average rewards from the probability distribution given the data that we have seen for each action. And then we take the average of these sampled average rewards, and we choose our next action based on this R hat of A. If we want to look at coins, then we can think about the probability with which a coin shows a head versus a tail, and that coin might be biased, so it might not be 50-50, it might be some success rate that we don't know, and we want to estimate this. And for this we can specify this distribution as a beta distribution. And the beta distribution has then parameters theta, which is then the average reward, and alpha and beta. And alpha is going to be the number of heads, so alpha minus 1 actually, and beta minus 1 is going to be the number of tails. But we will see that in an example just in a second. Before that, we need to understand what Bayesian learning is and how it works. Now, Bayesian learning is based on the object that we want to know. This probability distribution given theta, the true success rate, for example, that is something that we don't know and we want to learn. Now, because we don't know what the success rate is, theta could be a vector actually, and in the Gaussian model it could have the average and the standard deviation. But here let's think about the Bernoulli variable that determines the R, which has then as a parameter theta the success rate. So to express uncertainty about that theta, we form a prior distribution and compute a posterior distribution that takes all the information that we have seen so far to model the uncertainty about theta. And we use Bayes' theorem to update our priors. And so this gives us this formula here. So the prior P of theta is multiplied with the likelihood. So the probability of the data that we have given theta. And then we get a posterior distribution that is an updated prior. So with this machinery, we can predict the distribution of the next reward, having seen reward 1 through T so far. And that's also just this probability given the theta to get the reward, so the true success probability weighted with the posterior. And because we don't know what the right theta is, we just try out many thetas and get this posterior distribution. But we are not interested actually in the distribution over the next reward itself, but about the distribution of the average reward, capital R, for each action A. And now if this theta includes the mean, well, then we just need to write this up as the probability of observing this average reward given our data as a posterior distribution. So this compares pretty well to the UCB case, where we have also used a moment of a distribution, the upper limit, the upper bound, to model our uncertainty. But here now we use, in the Bayesian setting, the whole distribution. So we model the complete distribution, which allows for much more flexibility. Now consider a coin example. So we have two coins. We don't know the success rate or the rate with which they show head. So we model the average number of times that coin 1 shows head as this probability. And for coin 2 as well. So we want to maximize the number of heads in D flips. So which coin should we choose? The one that is better, but we don't know that, so we need to learn it. Now whether it's a head or a tail is this R of C1. That's a 1 if it's head and 0 if it's tail, and also for C2. And so those are the nully variables because they're binary. They take 0 and 1. And they can be parameterized by their mean. So the probability given this theta is just this average. The theta 1 would be then the average reward observed, the average number of times we see head. And the same for coin 2. Now, if we form a prior belief, we can model this by writing up the beta distribution. And the beta is nice because it has a conjugated prior. So that means that the posterior will be better if the prior is also better. And here we see also the average. The average is the number of successes alpha, the number of heads divided by the total trials, so the success rate. And once we play more often, this becomes more peaked. And in the beginning, it's completely flat. Now, if we have this prior distribution, we can, after a coin flip, multiply the likelihood of having received a head with the prior belief to get a posterior belief. And if we do that, the probability of seeing head given theta is just theta. So we increment actually this hyperparameter alpha by 1. For the tail, if we see a tail after the flip, we multiply the prior with a 1 minus theta, and we get an increment of the beta with 1. So the Thompson sampling algorithm works as follows. So we sample from the posterior distribution D draws of the average mean. And then we take the average of this average, and for the arm with the best average of the average, we execute the next trial, the next experiment, and we receive the reward and update our posterior as in the Bayesian learning. Now, how does exploration and exploitation work with Thompson sampling? To understand this, take a look at this example here. And actually, I have an animation that we can watch. Here we have a setting with 3 arms with different true success probability that we don't know in the beginning. So you have here the top arm, the middle arm, and the bottom arm. And the success rates could be from 0 to 100%. We don't know. Yeah, so that's why we have betas that have 1 and 1 and give us a flat line. That models the uncertainty. It means it could be either 20%, 0%, 80%, 100%. We don't know, yeah? For each of the arms. But actually, the true ones, we don't know that. The algorithm doesn't know the true success probabilities, but I have put the vertical dashed black lines here. For the top arm, it's 35%, for the middle arm, 60%, and for the bottom arm, it's 40%. So now if we play one round, we get a win for the middle arm, so the success rate could not be anymore 0%, but it could be 100%. Let's play it again. We get another success. Great. And another one. And another one. Oh, now we have a fail. So, well, it cannot be 100% success rate anymore, but 80% is possible. The algorithm then selects another arm just because it drew a sample and this turned out to be the best arm, and then repeatedly tries different arms. And you see here there is still some uncertainty about what the true success rate is. And now moving on in time, the Thompson sampling selects more often the arm that works better, that has a highest success probability, and fewer times the one that has a lower success probability. And you see that after a while it actually does a great job of getting the best arm, and also getting a reduced uncertainty about the true success probability. And you see here the numbers, alpha and beta, are pretty high for this middle arm, but pretty low for the top arm, which really performs not that well. And you have still a large uncertainty, but you also don't want to play that too often because you lose too often with this arm. Now, if you compare Thompson sampling to the greedy strategy, you can see that the greedy strategy just takes the observed rewards in each time step and samples from this. And Thompson sampling does this as well, but also samples from the posterior distribution of the average rewards, given the data that we have seen already. It then uses these to form an average of these draws, and the greedy strategy only takes the observed averages in the over time to form an empirical mean. Then both select an action based on their measure of success. So for greedy strategy, it's just the empirical mean over time. And for Thompson sampling, it's the average of the sampled averages, which is the basis. So the greedy strategy does not have any exploration because it always only selects the best arm. But Thompson sampling actually does have some exploration because we have seen the distribution is, if it's dispersed, you might draw one average reward at a very high end of the distribution and the next time at a very low. So there's then a little bit of exploration here. But if you play, if you draw a lot of samples, then you get more close to the average, and then there's fewer exploration. And that's actually what a property is of Thompson sampling. So there are two things that actually make exploring less often. That's the number of data that we have seen. So the more information we have, the more peaked and compressed our distribution is. And the second thing is the number of samples that we draw. With the more samples that we draw, our distribution still stays dispersed because given that we don't have new signals, but we get closer to the average, to the mean. So then we have less exploration here. So in practice, people set the draws to 1 to not shut down exploration too much. So that's actually what is up also here on this slide. Other than that, Thompson sampling converges to the best arm, and actually it correlative regret grows with logarithmically. So it's on par with UCB and epsilon greedy. Now here are some references if you want to dive into some practical applications as well with Thompson sampling. Let's just summarize what we have learned about Thompson sampling. Thompson sampling models uncertainty, the whole distribution, not only the expectation or the expectation and upper bound. It uses probability distributions to do that. It samples from the posterior distribution for each arm to get a reward distribution. And it selects the arm with the highest sample value. So the posterior distribution is updated after each observation. And doing this achieves log regret. So Thompson sampling, especially in its form in contextualized bandits, is heavily used in practical applications, for example, at Google, Amazon, Facebook, Salesforce, and Netflix. And here are some of the papers these practitioners have written about Thompson sampling. Thank you for watching and see you in the next video.